My name is Ronit, and this is my lab 5 for physics 2. So in this lab, we did a magnetic braking experiment using Faraday's law, and the purpose was to analyze the effect of the magnetic field created by a conductor solenoid on a magnet or a magnetic dipole falling through it. And I found a calculated time of 1.689 seconds and an average experimental time of 0.888 seconds. In the experiment, we labeled the north pole of the magnet. We used a magnometer to find that and then taped the north side. And then we dropped the magnet through a roll of aluminum foil. We recorded the times it took for the magnet to fall through the roll, and we then made a computational model on GlowScript to recreate the same experiment and find a calculated value to compare our experimental values to. So some fundamental physics principles needed for this experiment are the principle of magnetic flux, Newton's second law, that a net force on a mass is equal to the mass of the object multiplied by the acceleration of the object, Newton's third law, every force has an equal magnitude in the opposite direction, which is a reaction force, Faraday's law, the Biot-Savart law, and I have some of the equations on the next slide. The magnetic field of a dipole and Ohm's law. And Ohm's law is V equals IR. And here's some other important formula that you need specifically to make the computational model. So some assumptions my group used are that we assumed that there was no air resistance on the following magnet. We treated the roll of aluminum foil in the model as a collection of charged rings. And we assumed that there was no other significant external magnetic force affecting the magnet that could have affected the force on it and the time it would have taken to fall through. So here's the link to my computational model, and the model worked properly, and the time I got at the end was 1.689 seconds. Here's my code for the computational model I made. So I'll just scroll through. I changed various values like the length of the tube, the width of the foil, and the inner radius of the tube to the values we measured in our lab. Also, the mu mag from lab 3 at 3.20 and the mass of the magnet at 0.023 kilograms. Most of this GlowScript program was done for us, but I also created the function to calculate the magnetic field, magnetic flux, and I calculated the current in the ring. I calculated the force of gravity, and then somewhere down here the net force and the force of the magnet. And then I found the magnetic field at each ring and then the magnetic force on the ring, and therefore using Newton's third law, the magnetic force on the magnet. And finally, I found the velocity and position of the bar based on two of the equations I showed you earlier in this presentation. So additional questions and conclusion. So if the resistance of the conductor were reduced as close to possible as zero, the reduced resistance would lead to a much greater current due to V equals IR. And this increased current would induce a much greater magnetic field and therefore force upward on the magnet. This would result in the magnet taking a longer time to fall through the tube because that force is opposing the motion downward. If holes or slots were cut into the tube, I believe this would mean less of the conductive material, and it would mean technically less rings and less current, which would result in a less strong magnetic field, which again is opposing the motion, and therefore would actually let the magnet fall through the tube faster. So, thank you for watching, and have a great day.